Okay, good morning. This is Professor David J. Delosreyes. Okay, it's October 3, 2023. The time is around 3:17 a.m. Okay, my topic for this session will be a continuation of my subject matter, alternating current machines. And we are now on lesson number 29. The title of the topic is parallel operation of transformers with unequal voltages, meaning transformation ratio number 1 is not equal to transformation ratio number 2. The topic for this morning will be a very important topic under the study of electrical engineering, because design engineers for what they call this distribution lines, actually this is their problem. If there will be a circulating current when the load is disconnected, the distribution transformers might get burned. Okay, because there will be a circulating current. So if possible, okay, they will try to design a distribution setup in which there will be no circulating current, or the circulating current will be minimum maybe. But the best possible solution is actually the circulating current should be zero. Okay, so the transformers will not get burned, because there will be a circulating current if the ratio of transformation of the uh, transformers that are connected in parallel are not equal. Okay, let's proceed. Alternating current machines, lesson number 29. The title of the topic is Parallel Operation of Transformers with Unequal Voltages. That is, the ratio of transformation E1 is not equal to E2. For a step-down transformer, ratio of transformation is actually the primary voltage over the secondary voltage. Okay? So if I will try to place subscript 1 over here, this should be subscript 1, meaning for transformer number 1. A ratio of transformation considering transformer number 1 is actually A1. This should be BP1 over BS1. It should be the primary voltage for transformer number 1 over the secondary voltage for transformer number 1. So if this is 1, this should be 1, this should be 1. P here represents primary, S here represents secondary. And the other formula will be, it's the same. E2 will be equal to BP2 over BS2. Okay? So the relationship of the ratio of transformation for number 1 and number 2 is given by this formula here. Okay? So our problem is, if A1 is not equal to A2, if they are not equal, meaning their primary and secondary voltages are not equal, there will be a problem. There will be a big circulating current in which, at the so-called no-load condition, the circulating current will circulate among the transformers, okay, and they might get burned. Okay? Okay, let's try to bring out the circuit diagram of two transformers which are connected in parallel serving a load. This load here is, this should be a concentrated load maybe, but it is represented by a value single C sub L, and this should be equal to maybe 50, the impedance load of 50 households or 10 businesses maybe, which is being served by two transformers which are connected in parallel. So for the meantime, we place the load as just simply load. Okay? Okay, the impedance will be C sub L. Okay, I will try to erase this one so we could visualize the summation of the voltages. Okay, this will be the circuit diagram. This is BP over A1. This is the equivalent impedance referred to the secondary for transformer number 1. So this number 1 subscript refers to transformer number 1. And so with the current, meaning the secondary current given by transformer number 1. So that's I is 1. And the second transformer will be the input voltage coming from the primary side will be BP over E2. Okay? And it got an impedance of CE, okay, S2. So this 2 here refers to transformer number 2. Okay? And the current given by this transformer is actually designated I sub S2, meaning secondary current given by transformer number 2. And the voltage across the load, across this, is BS, is the secondary voltage. And this is actually equal to the load voltage. Load voltage, this is the one that goes to our houses, BL, secondary voltage. Okay, let's try to bring out the summation of the voltages. What will be the significance of this derivation here? We are interested in the circulating current, okay, when the load is disconnected. If there is no load, the figure will be something like this, right? This should be the voltage coming from transformer number 1 in the secondary. This should be the voltage coming from second transformer on the secondary side. Whether we like it or not, there is an impedance on the secondary for transformer number 2 and number 1. So when the load is disconnected, okay, no more load, the figure will be like this. So if you try to see it, there will be a circulating current, right? We remove this load, the figure will be something like this. So whether we like it or not, there will be a circulating current if the value A1 is not equal to E2. Okay? Because if A1 is not equal to E2, let's try to see it. If this is 2,300 and this is 10, okay? And this is also equal to 2,300 and this is 10. Try to see it. If the voltages are equal and the ratio transformation are equal, okay, what will come out here will be 230, right? This will be 230 and this should also be 230. Okay, so it seems we got a voltage here of 230 and there is 230. Okay, they will try to cancel out each other, right? It's just like you got a 5 pounds on the other side and you got another 5 pounds on the other side. And if you try to make the two forces together, right, there will be so-called equilibrium. But on the current, if we are talking current, if the voltage applied here is 230 and the voltage applied here will be 230, there will be no circulating current. The problem is, assuming this is the ratio transformation here is 5, so this will be greater than 230, assuming this is equal to 400. So if the voltage here is 400 and the voltage here is 230, there will be an unbalanced voltage. This is stronger than this one, so whether we like it or not, there will be a net voltage, right? 400 and 230, they will try to fight each other. There will be a difference of around, how much? 230, 170? It's 170. Right? 170. So that difference in voltage will produce a current, and that current is actually the so-called circulating current. Okay, I will try to erase this one. Okay, let's go with the derivation. Because the main purpose of taking the summation of the voltages here is actually to bring out the formula and how to compute for the value of the circulating current if the ratio of transformations are not equal. There will be two cases, case number 1 and case number 2. These are the formulas, right? So from here, you could visualize that if E2 is equal to E1, this will become 0. Bs times 0 will be 0. So 0 over a number, the circulating current will be 0. If they are equal. Even on the other side, if E1 is equal to E2, E1 minus E2 will be equal to 0, right? So 0 times Vs will still be 0, and this value here will not be 0, right? It will become a 0 over a number, and a 0 over a number will still be 0. So the base condition for the circulating current to be a good current is that when E1 is equal to E2. But there is no such thing as what you call this, if you try to use two transformers, we are lucky if E1 is equal to E2. Sometimes they are not equal. That's why we are interested in the value of the so-called circulating current. Okay, let's try to bring out the derivation. Considering this loop here. Okay, this is the tracing. Minus to plus, so that's Vp over E1. The voltage across this is plus Vp over E1. The polarity is from minus to plus, this plus. This is the voltage drop. The voltage across this is the current passing and the impedance it passes, right? So this is minus IS1 times the equivalent impedance CES1. And the voltage across this, it should be a voltage drop. Right? And the voltage across this is Bs. So this is minus Bs. And this should be equal to 0. Solving for Bp, Bp will be equal to, we place this on the right, we place this on the right, so they are now both positive. But A1 is underneath, so Bp will be A1, okay, times the sum of IS1 CES1 plus Bs. We call that equation number 1. Well, we take this tracing here, this one, right? The voltage across this should be minus, this is plus, so a minus to plus, this is plus Bs, okay? If the trace is like that, this current is against the trace, right? So this is minus, no. Is it correct? Oh yeah, it should be plus. Plus IS2, okay? The voltage across this is the product of the current passing through it times the impedance. So this is IS2 times the quantity CES2, okay? It's a plus because it's against, right? This is a drop because it goes with the direction, right? Since our tracing is like this and this is against, this should be plus, right? And the voltage across this, okay, the polarity is from plus to minus, so this is a voltage drop, minus Vp over A2, and this should be equal to 0. So computing for Vp, we'll compute for Vp, we place this one on the right, so this 2 here will be a summation, and this should be multiplied by A2. So Vp, by simplifying this one, will be A2 algebra, right? Times the quantity IS2 CES2 plus Bs plus quantity, we call this equation number 2. Right? What's next? Consider this junction here. The current entering this junction is IS2 and IS1. The current going out is actually the current going to the load. So meaning to say the current coming from transformer number 1 plus current coming from transformer number 2 should be equal to the load current. That's equation number 3. That is IS1 plus IS2 equal to IL. And we call this our equation number 3. Right? This is the current coming from transformer number 1 on the secondary side. This is the current coming from the second transformer still on the secondary side, and this should be equal to the load current. We equate equation number 2 and number 1 because this is BP and this is BP, so we equate BP equal to BP, right? So BP using equation number 1 is this one, A1 times this quantity here, IS1 CES1 plus BS close quantity. The value of BP by using equation number 2 is this one. This is A2 times the quantity IS2 CES2 plus BS. Okay? We mark this one as very important because in the computation of the circulating current, we will be using this equation here. Okay? The condition is this. When the load is removed, okay? If we try, okay, I will erase it here. If the load is removed, no more load, right? Will there be a circulating current? What do you think? There will be. If this voltage here is greater than this voltage, there will be a circulating current. And if this voltage here is bigger than this, there will still be a circulating current. Okay? So the first case scenario is this one. If this one is bigger, this is smaller, the circulating current will be this. That's the direction. But if this voltage here is bigger than this, the circulating current will be in this direction. Right? Counterclockwise. The first one is clockwise. Right? So when the load is removed for case number 1, that is when A2 is equal to A1. Okay. When A2 is greater than A1, okay, this is bigger because A1 is smaller, right? So the circulating current will be this. So IC is clockwise. It is this. Case number 2. When A1 is greater than A2, okay, so meaning to say this is smaller, so this will become bigger, okay? Oh, smaller. When A1 is greater than A2, this will be bigger. So the circulating current will be in the reverse direction. It is this. It is counterclockwise. Okay? Those are the two possible scenarios. That is when the load is removed. It's very dangerous because when the load is removed, if these two voltages are not equal, whether we like it or not, there will be circulating current, and that circulating current might burn the transformers. Okay, let's proceed. For case number 1, when A2 is greater than A1, okay, when A2 is greater than A1, it's the first condition. This is IS1, right? This is IS2. When A2 is greater than A1, the current is counterclockwise. I place it here. IS1 is equal to IC. Okay? IS1 goes with the direction of the circulating current. This voltage here is greater than this. And the circulating current is against IS2. So we place it here. IS2 is actually negative IC. Okay? So if we try to put these two values here, back here, okay, what will come out? It should be A1, IC, CAS1. Okay, IS1 is actually equal to IC, first condition, plus BS equal to A2. This IS2 is actually negative IC for case number 1. So this is negative IC, CAS2 plus BS. Okay, am I still on camera? And if we try to simplify this one, it's just pure algebra. We combine similar terms. there is an IC here, this is an IC here. So this IC term, we put it in the right, we combined it with this IC, and this E1BS, we put it on the left, right? This is plus, right? So when we put it on the right, it now become minus. So IC now will be equal to BS times the difference of E2 minus E1 all over E1C is 1 plus E2C is 2. This is the deciding factor here. E2 is greater than E1. Okay? So if E2 is greater than E1, there will be a value here. It will not be 0. Right? So the magnitude of the circulating current, just in case E2 is greater than E1, is given by this formula here. This symbol here is absolute value, meaning don't use the J, just use the magnitude, right, for the impedance. Because the impedance is like this, right? This is J, this is R, this is X. Just use the absolute value of the impedance, okay? But don't use R, don't use X, use the absolute value. Because J is different from R and X. J is actually the vectorial sum of R and X. So this sign here is absolute value. So for case number 1, the numerator got a factor A2 minus A1. And for case number 2, it will be the reverse. We'll just follow this one, okay? Because A1 is greater than A2, it will become A1 minus A2. That's for case number 2. Okay? These are still absolute values. So the two formulas on how to compute for the circulating current when the load is removed is given by formula number 1 and by formula number 2. And by formula number 1, A2 is greater than A1. And for formula number 2, A1 is greater than A2. So if you try to see it, this is A2 is greater, so it is A2 minus A1. For case number 2, A1 is greater than A2, so this is A1 minus A2. This is in amperes. So actually, you could compute how much will be the circulating current just in case the transformers don't have similar voltages on the primary and the ratio of transformation are actually different. Okay, that's it, guys. That's the way how to compute for the circulating current, okay, for the parallel operation of transformers. So when the load is removed, that's a very dangerous one. There will be a big circulating current, okay, which will circulate, okay, and it might burn the transformers. Okay, good evening or good morning from Los Angeles. Professor David J. DelosReyes.